Hey, what's up, guys? Here we are back again for some more of the HVAC optimal start math. Like I've said before in all the other videos, like we're studying mechanical engineering theory, some of these math models defined in research, and how we can feed in temperature of a HVAC zone, set point, and a schedule from a building automation system, and then these math models will start predicting minutes. And there's read the paper in here by the Pacific Northwest National Labs. These are the models that we've been going off of, and then we've been studying model 0, which is just like a typical model. That's just a degree per minute, a linear model. Probably most common in building automation. And then there's this fancier model, a quadratic equation that's talked about using the delta temperature and creating a quadratic math equation. The delta temperature is the zone temperature that's drifted when the building's unoccupied compared to the occupied set point. And then there's also model 2, which is the linear degree per minute model with some kind of a ratio defined that factors in outdoor air temperature. Model 3, which is a multiple linear regression model. So I created a couple bonus days in the program. So there was a 50-day crash course created by AI, and I wanted to get a little bit more deep in the weeds in what would it be like to fit a model using multiple linear regression, the math basically that goes behind the scenes, a lot of matrix algebra, etc. Because some of the control systems that this runs in, we don't have like math libraries to work with, like a NumPy or a scikit-learn that can hide a lot of the complex matrix algebra. So we did that in a week crash course of bonus days, which could be its whole college semester in its own on the math that runs behind the scenes here. And then also, I think the next set of 7 days of bonus material is this. It's Model 4. So Model 4 is a first order thermal response model. So it's basically, it uses some logarithmic math behind the scenes, but first order, getting into some of the calculus, the derivative, so we'll be kind of looking at this behind the scenes too. So I also have this, which I've been showing in the Niagara building automation system. All 4 of these models are running, so I've been kind of showing this a little bit here and there, some screenshots, and this model 2 is giving me the best performance. But there's not a lot of data in it yet. But this is actually giving the best squared error. So here we go. So I might even get into this, maybe going beyond, and then kind of playing around with some hybrid models, perhaps hybrid model between 3-4 and maybe a machine learning thing. So that's coming too. Here we go. Okay, so we're going to the lessons. We've done the bonus days, first week of bonus days. So let's get into bonus day 8, which is model 4. And let's give it a try. So model 4. So here we go. We're into this, moving into these first order response models. I think maybe we could just leave it at that. Okay, so goal is to build a mental model for first order response. The temperature error shrinks by the same percentage of each sample. Model 4 in the paper uses a first order response model to predict time to reach set point. Define error. So Cooling will be zone temperature minus temperature set point, and heating air would be temperature set point minus zone. Makes sense, so I guess it'd be a positive number. Either way, the air is how far you are from set point. First order response says every time air gets multiplied by the same number. So if the, let's see, C, what is C here? I think it's just expressing decay, I think. Decay is good. No decay. If it's greater than 1, then it goes the other way. It doesn't decay at all. So kind of similar to machine learning concepts, I guess. When a rooftop unit starts, the first few minutes often have big progress, and then it slows down near temperature set point. That slowdown can be approximated by the percentage improvement per minute rather than a constant degree per minute. That is the first order response. Often looks more realistic than linear models. So I think like what it's basically saying is like sometimes let's say like a linear would be just like a line, like a perfect sloped line, and then this first order, it would be kind of like sloping, like a really exponential like look to it. So it'd be go up, really drastic, and then really starts to taper off as you get towards some kind of equilibrium. So I think this is like what we're kind of getting into, these first order models. Okay, so run this little bit of code here and try a micro exercise. So this is all of our matrix algebra by hand, which we did the last go around, which AI definitely helped. Like I said, it could have been its own college semester in that, and then some, so we kind of just briefly went over it. So I think I also need to drill into the lessons there, because this is actually some AI made some kind of helper scripts, which is kind of cool. So here we go. So if we do Python math lesson script. All right, so what is this trying to do? So it's trying to simulate first order errors. 10 steps. Maybe we can even play around and put that to 100. What will it do? And it looks like a number gets like this. So I think it might be kind of fun to play around with. We could even do plot data equals, let's just say a list. And then I think we could even do, so we'd want to see what this looks like in a curve in the plot. So we could do plot data dot append error e. That's our error here. So whatever this is doing behind the scenes, it's kind of generating this kind of cool looking thing. And then I think I'm just going to cheat here and go to Python import matplotlib pyplot, something like that. Can't remember the exact import. Copy U. And now we have plotting, so I think we can just do plot data dot plot. Oh wait, so we import matplotlib.pyplot as plt, and then we do plt dot plot. I think it's something like that. This is going to error out. have to do here now? Let's just Google it. Let's just do AI mode. Since ChatGPT, plt.show. Okay, so if we try this. Okay, so this will return, so it looks like the matplotlib expects data in like a list form. So if we just do, put that in here, I almost think we can just go like that too. All right, let's try this. So this is, we're importing the matplotlib as PLT. Looks like we need to prep our data, and then that doesn't look like it's going to work either. So I might have to run that separately. And we do just have to go like this. plt.show. Thought you could cheat, but I guess you can't. Here's our plot. Hold up, I think it's on the other screen. So here we go. So this was like that kind of decay that we were talking about. Kind of has that nice curve, and if it was perfectly linear, it would have been like just like a straight 45-degree angle line. So okay, so getting back into our lesson. Close U. Try changing this value for the decay. Which one reaches set point faster? Well, I guess for one thing, I changed this to. Let's try this. Which doesn't really show much. I think you can get a better representation if you do it the other way. So let's just run this again. So this would be, I guess this is our units of temperature on this side, and then this is steps. So 100 steps. So it looked like it got to the set point, I don't know, maybe around 50 steps. So it's asking us to change that to a different value. Rerun. Ooh, yeah, different. So like this got down here much faster. So I guess if this is trying to shoot a set point, what they're seeing for, this lower value on here takes quite a bit longer. So if we do 0.96 for something fun to try, then it'll probably be drastically the other way. Yeah, much more of like a shape to it like that, so cool. I think like this model might get into fitting that whatever that value needs to be. I think. Don't quote me on that. But let's see what the lesson tried. If the air starts at 8 degrees, what does 10? Okay, so we decided that the lower number is faster. If the air starts at 8 degrees, what does 10% improvement per minute mean? So, yeah, that's, wow. If I put that, that's almost like a perfect triangle again, or a perfect line. So this was 0.85. Then I think this one is 8 degree air. I don't quite understand this question. So If the air starts at 8 degrees, what does 10% improvement per minute mean? So I guess that would be 10% improvement per minute. Yeah, how would you say that? I know what it's trying to ask for. So that would be, oh boy, let's cheat. We can use ChatGPT again. Let's see, where were we? So that was our chat. I'm just gonna add, go back in here, give our AI some context. Let's see, so I'm just gonna say day 8 on the question, okay, so 10% improvement. I feel like that's so hard because like these lines are constantly changing. It's not linear. It would be really easy to calculate if it's linear, like a 10% improvement would be perfectly linear, but now we have to deal with this curved format. I'm just gonna say 10% improvement. That would be, okay, so we have to, if we turned error into a percentage, then at each time step, I guess it depends. It depends on how far away you are from setpoint, because it is not linear but follows a first order curve. Alright, let's just see what it says. If you're thinking about it correctly, the intuition is almost correct, but if the error starts at 8 degrees, does 10% per minute mean? It does not mean the temperature changes 0.8 degrees per minute. That's like a linear model. Model 0. Each minute the error is reduced by 10% to whatever error remains. Yeah, cool. So that's the big takeaway. Each minute the error is reduced 10% of what error remains, and I think that's why that's whatever error remains, it just gets a little more, a little less, just like what it's trying to show here as it nears set point. So looks pretty cool. So this is neat. This makes me think of a LinkedIn post that I saw lately. In your own words, state why first order models slow down near set point. Okay, key takeaway, first order response. Error shrinks by a constant ratio each step. That is correct. I'm just going to go on LinkedIn because I saw this post just the other day that I thought was good. I can't remember his name. Okay, so here we go. So Andrew Holden seems like kind of an interesting person. Does a lot of HVAC work and a lot of electronic stuff, which is pretty cool if you get into hardware, which I think is really hard to do. Electrical engineering concepts and PCB design, pretty neat. But he posted this the other day. Differential equations are everywhere. The left image shows what happens to a supply and return air temperature of electric furnace over time after you cut it on. Sorry, I had my probes assigned backwards. The first time, supply temperature. So he's talking about measuring resistance of a temperature sensor, like if you got under the hood of how you calculate the temperature value from resistance. At any time a physical system's current state impacts its own ability to change, you get these exponential looking rise and fall curves. I think of them like this might be the best way to develop an intuition of first order differential equations, just like what we're studying. So the same math emerging completely different forces and mediums. The capacitor develops electric field between its plates and that becomes stronger as it charges. So he's talking about we're doing the same thing. So he's talking about a delta temperature. So like electric heat comes, any metal contained within the supply will, especially blah blah blah. Hold up, sorry. The HVAC surrounding elements acts as a thermal heat sink at first, meaning there is less heat available to transfer into the airstream itself. So this is why the heat transfer is tied to differential between temperatures. When heat is first energized, the differential is large. The air temperature increases rapidly as the heat differential decreases. The elements warm up and down. This is pretty cool. So this is the same thing we're studying, but in optimal start equations. So like, I think what is measuring is like if you would turn on a furnace or air conditioner and then it runs real hard and it's a working, cooling air or heating air, and then you shut it off, that the time delay when you shut it off is following this first order differential equation, kind of a curve. It's the same thing that we're actually looking at in optimal start. So in optimal start, if you would try and condition the zone before the building starts and everything's running real hard and it's conditioning, as you reach set point, like the curve may look like this. They're everywhere, I guess, in the natural world. So pretty cool. I thought that was kind of ironic as we're studying the stuff that it is everywhere in the HVAC world. So thank you, Andrew. And that's all I have for today, guys. So going on to day 9 tomorrow, we will talk about exponentials, logs, and time to target. So fun stuff. I think this will get really hard again as we look into it might get really hard, just like these other bonus days where end up using AI quite a bit, because this isn't a whole college semester, so just a crash course, but I'm learning some cool things here, so hope you guys are too. Talk to you tomorrow. Have a great day.